Okay, we're going to go ahead and get started here as people still kind of trickle in. I'll make a few announcements before I turn it over to Andre. Welcome, everyone. If this is your first time joining us for a Georgia Arborist Association webinar, we appreciate you joining us this evening for this presentation. I'm Jessie McClellan, the Executive Director of the Georgia Arborist Association, and I'm so excited to bring this presentation to you this evening. If this is your first time joining us, then there are a few little housekeeping things that I like to go over in the beginning of a presentation. If you have questions, please put them in the Q&A, not the chat. I'll be monitoring the Q&A, and we're going to hold all of the questions until the end of the presentation. So feel free to drop those questions in, but we're going to just wait until the end. There's a lot of information to get through, and at the end, we'll leave some time for those questions. If you're here for CEU credit, I will be putting a link in the chat at the very end of the presentation where you can fill out your ASA certification number for CEU credit. That will be at the very end of the presentation. This presentation is being recorded, so if you have to step away for a minute or if there's something that you'd like to review, you will receive a copy of the recording by the end of this week. I'll have that sent out to everyone who has registered for this event. I hope that you'll join us for some of our upcoming programs, some that I'm excited about. At the end of this month, we're going to do our first quarter networking event. That is going to be at a brewery in Decatur. I hope that you can join us. If you're a member of the Georgia Arborist Association, I'll even give you a free beer. So please come out and join us for that networking event. Then we also have our annual PHC Day, and that's coming up on May 8th. You can find all of that information on our website. Those are some of our exciting upcoming events. We also have next month and May's webinars scheduled, so make sure to check out our schedule for the upcoming webinars. I'll include links for registration for those webinars when I send out the email with the video recording. So with that, I'm going to stop sharing my screen and turn it over to Andre. And, I think that he'll do a better job of introducing himself than I will ever do of introducing him. So I'm going to let him introduce himself. Welcome, Andre. Thank you for joining us. We appreciate you being with us this evening.
Yeah, thank you, Jessie. Hi, everyone. I hope everyone's having a great evening. And I hope we can make it even a little bit better with some exciting technologies regarding trees. Thank you, Jessie, for having me. Great to be back with Georgia Arborist Association presenting. Today's topic is surprisingly practical. Why is this surprisingly? Usually when I talk about these technologies, people think it's something that's 5 to 10 years out, but actually these all been around for quite some time, maybe also 5 years. So all of the things you will see today is something you can try for yourself even today. And I would definitely encourage you, to go out and play with some of them as you see fit. We're gonna go through 4 to 5 technologies, depending on how well we're gonna do with time, and then definitely gonna be some time for questions. Once again, my name is Andre. I'm originally from Europe, Czech Republic, but I've been living in States since June, specifically in New York City. But yeah, I've been traveling all around. Right now, I'm calling from Mexico. Next, I'm going to Australia for a conference. So I'm definitely back and forth. This presentation will be something, or my perspective is from someone who's been growing up around trees, but I had a chance to work in other industries and study something else actually. And I got back to trees about 5 to 6 years ago when we started at BN. AdBN is a company that's not a traditional tree care company, but we are developing technologies around LiDAR scanning, photogrammetry, AI, and these other exciting tools I'm going to be speaking about today. And for example, it's a tool AdBN, which is short for Advanced Biomechanical Analysis, that enables you to remodel tree in 3D, simulate wind loading and helps you figure out where's the weakest spot on the trunk and take necessary action. You can think of it as device test without expensive hardware. You can use just your phone to do that. It's also something, all of our technologies are not something that would replace arborists or people with boots on the ground. It's just another tools in their toolbox they can deploy in specific scenarios. We've been successfully deploying this technology on more than 50,000 trees all around the world. We have customers in Japan, States, Europe, Taiwan, so really all around the world. And our goal, why we started this and what we see is that these technologies helps to reduce unnecessary adult tree cutting. So that's our main focus. So yeah, if you are more into tree preservation, this tool could be something to look into. But yeah, today this is more highlighting like why I'm talking about these technologies. We've been developing, or I've been working at BN for the past 5 years. So I'm really sitting at that intersection of technologies and trees and research. This presentation and all you're gonna hear here is very much a group effort, even though I'm the only one speaking today. I just wanted to give a quick shout out our team. Since this picture, we hired 2 more people, so we are quickly growing. And why we are unique in this regard is that we have both tree guys, so most of them are PhDs in tree biomechanics, helping us with the research and making sure that these technologies are deployed correctly. And then we have strong technical team, so AI engineer, physics simulation, GIS specialist, and so on. So we are just putting these 2 worlds or trying to put these worlds together. So this is the perspective I'm going to be talking from today. And let me start with some of the insights I've gained as someone who is working in arboriculture, but was working in other industries as well. And one of them is that arboriculture is surprisingly isolated industry. I know that because since kindergarten, I had to explain everyone what my parents do. They are both arborists, and nobody knew what it meant. Obviously not the kids, but also not the teachers, not their parents, practically no one. You might have a same experience in your life that people are not really familiar in many cases what is arboriculture and that the industry even exists. But don't take my word for it. There was a great study done by ISA and Tree Fund surveying more than 2,500 people working all across the arboriculture industry. And public awareness and perception of trees and public awareness and perception of arborists were scoring the highest when they asked them what topics they should research more or what topics are important for them. Also, tree benefits and public awareness of trees was scoring as a number one topic in this regard. I will just quickly confirm, Jesse, can you guys see my screen? Yeah, you can. Awesome.
Yes.
Yeah, just wasn't sure. Amazing. So yes, arboriculture is isolated industry, unfortunately, and it can bring many disadvantages for the industry as a whole. One of them is that when people are not familiar with importance of the trees and that they should be taken care of, there is smaller revenue compared to the relative importance of the industry. Then it's hard to attract new talents. If people are just not familiar, this could be their career path. And there is definitely a slower technological development than in our other industries. And let me delve a little bit into this point because I'm from technological world partly. So let's check how technology is developed in the last 30 years. I'm about 30 years old, so I used my lifetime as a scale in this little case study. And the year I was born, Nokia 2110 was introduced to the market as a brand new phone. Ford Taurus was the best-selling car, I think, in the United States. Jurassic Park was just introduced to the cinemas in the summer. And the technologies consulting arborists had to analyze their trees was resistograph, tomography, and if they were lucky, or mainly in Europe, it was a pulling test. So now fast forward 30 years, where we have reusable self-landing rockets. We have autonomous vehicles being tested or being deployed actually in several US cities. And each of us carries a tool that has more computation than the whole Apollo mission in our pockets, mainly to share cat videos and memes. And this is all before the whole AI craze in the past 3 years. And which tools consulting arborists has to analyze their trees? It's resistograph, tomography, and if they are lucky, a pulling test. So I'm not trying to underplay importance of these tools and of the research that was done in the past 30 years, because I actually think our understanding of trees dramatically changed in this period. But I just wanted to show that the tools we are using to analyze them didn't really change. So why now? I think this is changing, why we are at the inflection point. First point is that arboriculture is actually becoming an important industry. People are, based on my opinion at least, waking up to that idea that trees are important and trying to deal with the trees more as a green infrastructure, not as nice to have. The technology is just getting so abundant and so cheap that they are just really hard to ignore at this point. So with the new technologies, there is also a problem that we definitely don't want to use technologies just for sake of using it. We don't want a gimmick, we want something useful. So for today's presentation, I'm going to use the same study from ISA and Tree Fund to create like checkboard to see if the technologies are helping with public awareness, so with communication, if they are helping with tree risk assessment and management, if they are helping with plant healthcare, in our case, diagnostics. It's also going to be validated if they are helping with mature tree care preservation, tree sciences, in our case, tree biomechanics. And these are going to be technologies and new products development. So I created these check marks for each technology we're going to go through, and I've added 2 extra. And first of them is that the technology should be accessible to everyone, and that it should be scalable, meaning it's not gonna take you an hour to analyze one tree with these technologies. And the technologies we're gonna look into today are photogrammetry, iPhone LiDAR scanning, a little bit of AI just for tree reconstruction, dedicated LiDAR, and as a bonus, if you're gonna stick with me to the very end, I'm gonna tell you why spaghetti might be a future of biomechanical research. So let's get into it. First technology is photogrammetry. So what is photogrammetry? Photogrammetry is basically reconstructing trees, or not only trees, but 3D objects based on 2D images. These images should be overlapping, ideally by 75 or more %. And with these pictures and correct algorithms, you can create a 3D model. We're going to be trying these technologies all on the same tree. So I'm playing a video from an app called Polycam. You probably don't hear the clicking sound, but you can see the pictures automatically loading when I'm walking around the tree. that are automatically collected. I'm not gonna torture you with the full video, but I ended up collecting a little above 60 pictures. And this was the result. So you can see very detailed, very realistic in 3D. So this is done by regular pictures and some smart algorithm. Only limitation of this model is that not really up to scale. There are setups how you can scale up and down the photogrammetry models, either based on real measurements or with some other tools. We're not going to go too deep into that today, but just if you are going to be using photogrammetry, make sure you are keeping in mind this limitation. So it's very nice, very good communication tool, but not really up to scale. I have here QR codes. This app is for free, so if you want to try it for yourself, you can download it for both Google Play or apps for iPhones. And the good thing is that you don't actually need even a phone to be using this app. You can use any camera, you can use drone, then you can take pictures, of the whole property, and anything that can give you a good digital pics that are overlapping can be uploaded to this software that helps you to reconstruct the 3D model. So I would say this is definitely the lowest hanging fruit in terms of access, that really anyone can use this to just improve their visualization and communication with their clients, like really to show them what's going on their trees. So from the perspective or from the checkboard, it definitely helps with the communication with the owner. It doesn't really improve tree risk assessment by itself, so it doesn't help with mature tree preservation. It doesn't really push forward the tree sciences by itself. And yes, maybe you can plug it with some AI models to help with disease detection. But this one is definitely not black and white. It's definitely accessible for everyone. And for time to collect the data, it would be around 5 minutes per tree. So you can also try, if you are holding your phone, why photogrammetry is not very precise. If you open your cameras, and if you have a phone that has the fisheye effect, where is the best visible the best, you can just open that, and you can just move with your camera around the room you are sitting in. And what you see on your display is basically that the objects are shrinking and expanding based on that, where they are on the display, right? This is called distortion, and it basically tells you that with different lenses, the objects can appear bigger or smaller, or have different distortion on the edges of the camera. The differences can be quite profound, even from a same spot of this example. How, for example, we work around it with our tool is that we implemented what is called phone calibration, where you just print out the chessboard, take a couple of pictures of the chessboard, and then the algorithm then automatically assume or calculate distortion of your lens and use it for reconstruction in 3D. But yeah, still, this is just for the rough geometry, not really for any precise measurement from the photos. So just keep that in mind. Okay, so the next technology we will look into is LiDAR-based 3D scanning. And there's going to be already some overlap with the tree biomechanics. So this is again a video how LiDAR scanning can look like. So you just start it, and you are trying to get rid of these colorful points, and you are just walking around the tree once, waving your phone up and down. There is my little sister crawling by. And even with a huge tree with huge open cavity like this, you can see that it took about 40 seconds to collect the data and create a 3D model, not from pictures, but from video and the LiDAR sensor. So what is LiDAR sensor? LiDAR is actually specialized hardware that measures distance between the device, in this case, your phone, and a reflection from the closest object. So it can create like a floating points in the 3D space and then project the texture from pictures as you saw on this tree. So it's actually a measurement technology. So its best feature it's that it can actually measure the objects you are looking at. The good thing is you can, but you don't have to use additional hardware because not sure if you are familiar, but iPhones Pro, anything from iPhone 12 Pro has LiDAR included. Unfortunately, not other phones. I'm not sure if there is some patent from Apple that's restricting other manufacturers, but it's been 5 years and nobody else implemented it. So if you have iPhone with 3 lenses, you also have a LiDAR scanner, and you can also go out and scan trees, starting today. I have 2 apps to show you. This is 3D scanner app. This unfortunately is not free anymore since I think last month. So you can use it. There is small fee for it. But it's very fast, and yeah, you can load the data really quickly. Yeah, again 40 seconds, and you have model like this. And the best part is, again, it's measured, it's up to scale, it's pretty reliable. I have here a QR code, unfortunately only for Apple users. In this case, even only for iPhone Pro users. But I have here also a free option I'm using right now, which is called Scaniverse. And it has basically the same functionality, but it's completely for free. So you can scan this one as well. So a valid question would definitely be how precise LiDAR scanning is, right? So I have here a case study and from Stefan Rust, who's German scientist, and he's been testing a new tomography device, which doesn't use caliper to get the sensors, but is using these boxes with a QR code. And even though this looks like a video, it's actually LiDAR scanning as well. And you can see the points popping up once it's recognized the QR code. So you can just walk around the tree, scan every sensor, and it would give you the geometry of the cross section, or at least of the suns in the app. So this was mainly a case study of how precise can LiDAR scanning be compared to manually collected data. And they found that there was only 0 to 2% deviation from the reality. So I would say that we would have bigger differences if we were all of us measure shrunk with or DBH with a tape than 2%. So I would say that LiDAR is pretty precise. I found another study that was specifically measuring iPad LiDAR, which has the same sensor as iPhone, as far as I know. And it was comparing it with terrestrial LiDAR, multicam, which is basically photogrammetry. And their finding was that the error rate was only 1 to 1.4 inches on a bigger tree. This LiDAR scanning doesn't really work on small trees. So if the diameter was under what was it, 4 or 6 inches, it wouldn't really pick it up, and it doesn't really work well in a poor light conditions. But other than that, the error rate was precisely 1 to 1.4 inches. So when we have precise measurements from LiDAR, then there is a valid question, how precise are the state-of-the-art technologies we are using today, such as tomography readings, right? Because with tomography, which is basically using sound to reconstruct these images, that's going to tell you if there is any cavity inside the tree. And you would use caliper, which is like a big digital ruler that's going to tell you how far from each other are the sensors. But the question is how precise it is on the inside and how precise is it on the outside, on the geometry. And there is not many studies on this, surprisingly. But there I found one that was testing tomography against the real cross-section of the tree. And they find that there was 90% accuracy of the damaged area and only 83% accuracy of the damaged area plus the whole cross-section. So it was way more accurate on the inside than it was on the outside. But actually, and now it's getting more to the tree biomechanics, the outside geometry of the cross-section can be way more important than the inside. So yeah, now we're going to go a little bit into the tree biomechanics. So tree biomechanics is basically stability of the tree based on its physical properties. So it's probably a little closer to physics than typical arboriculture. And it's all about risk mitigation and prevention of unnecessary tree removal. So it's about finding that right balance. And tree biomechanics is based on what is called triangle of stability, which tells you that there is some load, in our case, wind load or a weight of the tree, which is influencing the structure, the tree. And the tree can react either by its material, which is wood material properties, different species going to have different properties, and the geometry. And geometry is arguably one of the most important subject calculate with. Because I will just show you in a couple slides why is geometry so important in tree biomechanics. As you probably know, there is a couple of stresses going on in the trunk during the wind loading. There is compression by its own weight. There is compression on one side and tension on the other during the bending. And then there is growth stress, but that one's very hard to measure and not very significant. But even these two stresses are creating pretty complex model of what's going on in the trunk. And we can calculate this. We're not going to go as deep as going into the equations. I just wanted to show you one variable, which is section modulus, or W. And section modulus is describing us the importance of the geometry of the cross-section. I have here also as a Z, so it can be W or Z. So you can see that the relationship between area of the cross-section and the section modulus is that it grows exponentially when the area grows linearly. Here is an example just to better grasp the context, because our minds are not programmed to understand exponential growth. So you have here example of two cross sections with hollow cross sections of trees, or a tube in this case. One of them has 31.5 inches in diameter. The other has almost 40 inches in diameter. And even though the smaller one has significantly bigger area of the wood, so you would say healthy wood, The second one has same section modulus, just because how distributed is the wood. So in this case, it's further from the center. So it's resulting in that you would say about these two cross sections that they have same section modulus, or if everything else is equal, they would have same safety factor or same probability of breakage. So this tells us that the wood on the outside is exponentially more important than the wood on the inside, basically. And we have many ways to calculate strength loss based on cavities in trees, but they are all based on basic assumption that the cross-section is a circle or an ellipse, right? I would say most famous is 1/3 rule, but yeah, again, based on perfectly circular cross-section. But you know from the practice that trees, as they are getting older, their cross-section are getting more and more complex. So we have buttresses, we have open cavities or old branches and so on. So these trees where we are actually interested in tree biomechanics and understanding their biomechanics and their dynamics are rarely a circle or anything close to a circle. So this LiDAR scanning can actually help us to calculate biomechanics based on real shapes and not only oversimplification. But back to that tomography comparison. Yeah, so I have here a first case study, which was done on a lime tree. This first picture is how the crown was calculated for the wind loading. And then we did a couple of scenarios of just for the sake of comparison. So this tree had to be cut down. So you can see the leftovers here. And first, the cross-section of the tree was calculated as a circle with the same area as the real geometry. Yeah, so it's an oversimplification, but we've calculated section modulus and what is called a safety factor. Then we calculated how tomography would pick up the data. So we placed 12 sensors around the geometry. In a third case, we calculated the real geometry. So this is what you would get from LiDAR scanning from your iPhone. And in the last case, we did real geometry with what you would consider a significant cavity in yellow here. And when we compared those four scenarios, we've calculated, safety factor. And for those who are not familiar, safety factor is number from tree biomechanics that basically tells you that if it's above 150% or 1.5, the tree is fine. And the 50% is a safety buffer because we are assuming that tree biomechanics doesn't work with precise information. So in general, you would want to be above 100% and 50% safety buffer. So here on a real geometry, which was this one, the safety factor came out as 2.65 or 265, so well above 1.5. The circle, even though it was the same surface area, it had almost 40% error rate. So it was 40% overestimating the safety factor. Tomography, which is only a difference between this one and this one, was 23%. And the large cavity, which is the last slide, subtracted 31% of the safety factor, which again shows us that only a small differences on the outside of the cross-section can have similar effect as pretty large cavity for calculation tree biomechanics on the tree, right? So if we want to make any assumption about if the tree is safe or if there's high probability of breakage, based on that we detect cavity there, it's essential for us to also understand the outer geometry, because that's actually how the trees are responding with response growth and where it's growing a new wood. So yes, that's why something like LiDAR scanning in these cases is pretty exciting for the industry. I have here another case study. On the left, you see a tomogram. On the right, you see cut through the 3D scan from iPhone LiDAR in the same height. And as you can see, they are not overlapping very nicely. So that's just by how tomography or tomogram is reconstructed. It's kind of a black box. Each manufacturer has its own algorithm, which are not public. But I just wanted to show you they can be pretty off the real measurements, even when you collect the data correctly. In this case, it was 18% more healthy wood than anticipated by tomography, but because it was wood on the outside, it actually added around 40% additional safety factor of the stability. So, these more precise tools, even though it seems marginal, the couple of inches here and there, these can be really a difference between cutting down a tree or preserving it. Yeah, we in our team did way more than 10,000 tomography readings compared with real 3D scanning. And if we learned one thing, it's that with simpler shapes, it gives you the rough estimate pretty close. But as you go to more and more complex geometries, they would start shifting apart pretty quickly. And with a tree like this, you wouldn't even guess it was a same tree or same height of the tomography reading. Yes. So yeah, that was a little bit longer, but it was iPhone LiDAR scanning. So you can see that it can help you to communicate with tree owner way better, like showing same as photogrammetry. It can improve tree risk assessment when connected to other tools and algorithms. It can help with mature tree preservation, mainly in combination with tomography, and it can help us push forward the tree sciences like tree biomechanics. By itself, it also doesn't help with tree detection or tree disease detection, but it can be, again, connected with other algorithms. It's somewhat accessible to everyone. I would say the investment to old iPhone Pro is definitely worth it. And time to collect data is about 1 minute per tree. So very scalable. So we will check one more app that's using Gaussian splatters on your phone as well before we move to the next technology. So there is another app that is called Luma AI, and it enables you to create like whole tree 3D models, again, just based on video. So I call this like photogrammetry on steroids because it has same limitations, but it's just way better communication tool. I have here again example of the same tree. I'm not gonna bore you with the whole video, but I just walk around the tree collecting video, not single images. And the result looked like this. So yeah, pretty effective for the communication. But when you look closer to the data, it's actually even worse than with photogrammetry. The whole 3D model basically falls apart from the video. So yeah, that was one use case of AI in 3D reconstruction I'm familiar with. I give you also the QR code. I think the app is still also free, so you can use it on both Android and Apple. So feel free to scan the code. And yeah, basically same limitations as photogrammetry, so we don't gonna go too deep into that. One last technology I have here for you is dedicated LiDAR scanning with handheld scanners. This is first technology that's not accessible from your phone because your iPhone sensor has only reached about 6 feet for the scanning. So there's no chance you're gonna scan with it whole trees. But you probably came across of these things. They are mainly used in other industries, but finding their way to urban forestry pretty quickly and arboriculture. The good thing about LiDAR of this size is you can mount it on car, on a drone, or just use handheld device and just walk around the park and collect the data. And for example, for use case of tree inventories, it can be pretty effective. So this is potential output that you can get from walking or driving around the street. So it's just a mesh full of points, without additional context. But with the right softwares, you can find individual trees there and actually run like almost automatical tree inventory. So this is an example of one of our customers who collected this as a walk. He described it as a walk in the park, like 20 minutes walk with a LiDAR sensor in his hand to collect about 150 trees, which then he can get like the measurements, basic measurements from the LiDAR itself very, very quickly and easily. Yeah, I have here also, so you can use it to extract individual trees, and depending on the precision or on the point cloud density, you can also use it for biomechanical calculations, because you can get a shape of the crown from it. You can get a stem pretty precisely, again, depending if you are collecting it from handheld or from a car. So the precision can vary. But yeah, it enables you to create outputs like this, where you can communicate again with your customer on a whole tree inventory level and just select and work with annotation of the point cloud, show your customer where's the problem on the tree, show them, select the, for example, crown for pruning recommendations, and again, use this data for a recalculation, what it would have, what effect this would have on tree biomechanics and the stability of the tree. So this one's definitely of a higher price point than just a couple of $100. I think the cheapest ones you can get for starting for $3,000. The more effective ones for tree inventories are around 20-30K, and you can get to 120K pretty quickly when you are looking into car-mounted LiDARs. But again, it always depends on the scopes of your project. So if you want to do whole city scannings, like 120K doesn't seem as big of an investment when then you can collect the data you would be collecting for several years in a couple of weeks. So there is definitely use case for it in our industry already, and I think you will be hearing more about it in a coming months and years. So yeah, for dedicated LiDAR, I have here wrong time. Even with handheld LiDAR, they can definitely help with all the things we talked about previously. They are not as accessible because you have to buy additional hardware, and time to collect the data. As I said, you can collect easily 120 trees, 150 trees in 20 minutes with a handheld device. And from a car, we have a use cases of driving the cars around 60 miles per hour by the streets, and it would automatically pick up all of the trees on the sides. So I've scanned a little bit about what's the role of tree biomechanics and precise geometry. But yeah, I have here also one additional study just for your information regarding tree cavities, because we are in a great position where we are getting a lot of data from the customers, and we can do additional research on those data. For example, yes, I already described like what is a safety factor, but I also want to show you why it's important not to calculate just one safety factor on the trunk, because if we would assume, again, oversimplified circle for a tree, the weakest point would be always at the base. If it would be like a cone that is getting thinner on the top, the weakest spot would be somewhere below the first branches. But on real trees, the weakest spot can be anywhere on the tree, right? Depending on the tree's geometry. So it's important, to don't look on a safety factor as a singular number. What we, for example, are doing is reporting the safety factor every 0.3 feet on a trunk. And you can see it can vary from 400 to 200 at the weakest spot, in this case, 4.6 feet. So yeah, getting just one number doesn't have to be enough. And I just wanted to show you like what's possible when you have these LiDAR scans. So you can, for example, model theoretical cavities in the tree and calculate what if this tree would be hollow, how it would influence the safety factor. And also model like pruning scenarios. If you reduce the crown by a certain amount, how much it would help the safety factor. So this is all the cool stuff that this 3D scanning opens for the industry. And yeah, I wanted to show you the case study, or not the case study, but more research on a subset of our data, where smaller cavities basically don't move the needle at all for the safety factor. So the tree basically doesn't care it has a small cavity at the center, as long as it has enough wood on the outside to support it. Even cavities like these can reduce the safety factor by very small amount. But we did an analysis on 130 trees and did some relationship, or we were trying to find some relationship between variables of the measured values. So this is gonna get a little bit more technical, but I will try my best to explain it. So the assumption was to figure out if trees actually care about open and closed cavities when you can scan them with your phone. So imagine, 130 trees, all with an open cavity where you can stick your phone and scan it from the inside. Some parts are open like this, some parts are closed because they don't no longer have opening. For example, if you turn your phone and scan from above. And the question was how much the cavities on average are influencing the results. And the results was that presence of the decay in a cross-section with lower bearing capacity is that the weakest spot on the trees with open cavity was only in 31% of the cases. So in a 67% of the cases, the weakest spot was somewhere else than at the open cavity part, right? So cavity doesn't necessarily mean that the tree has a problem, or it can have another problem, but not at the open cavity point. So this is something definitely an interesting finding from the biomechanical perspective. Then we were trying to figure out which of these variables are most dependent on each other. So again, we were validating if that the tree has an open cavity has meaningful impact on a safety factor. And the thing that has actually highest impact on the presence of an open cavity was a height of a center of gravity, right? So it basically the height and the size of the canopy were the most important factors determining the height of the weakest spot on the trunk. And interesting outputs was also found from what has the lowest correlation. So which variables are influencing the least that the spot or the presence of the lowest safety factor. So yeah, these are the columns of the safety factor, and presence of an open or closed cavity had actually the lowest correlation with the safety factor altogether. So in other words, we didn't find any significant statistical relationship between that the tree has an open cavity and that it should have a lower safety factor at that point, because just how well trees are usually reacting with reaction growth to it, sometimes overdoing it. So yeah, that's why we didn't find any significant relationship between these variables. So I would say trees can be way stronger than we sometimes give them credits for, and these new technologies can definitely help us not only to find out which trees could be problematic, but also to communicate it with a tree owner or tree manager. Yes. Okay, so we basically, I will just check time. Yeah, we have still a couple of minutes. So we went through a couple technologies and we validated them if they are beneficial for public awareness and communication with the owner, if they are helping with tree risk assessment, plant health diagnostics, mature tree preservation, and tree biomechanics. And now I have a bonus topic, as I said, telling you why spaghetti might help with biomechanics research. And sorry to all pasta lovers, but I wasn't talking about food, but I was talking about a new way of reconstructing trees with in 3D. Because right now the tree biomechanics is basically looking at individual cross-section and calculating the breakage resistance. These spaghetti or strand elements method would enable us to reconstruct trees and program each strand's physics separately to help us create real models of wood and how does it behave. So we can literally start breaking wood in the 3D, so it doesn't have to happen in a real world, and with different intensity, but also with different forces, so twisting, bending, shredding, and see if these models are close to the reality or not. So this is very promising space in tree biomechanics because it could also help us to reconstruct the whole trees with it and show like a heat map where the tree is being stressed when you just wiggle with it a little bit, or when you simulate wind loading, for example. And you could also simulate like trees from reality to the breakage. So you can literally pull them to see under which condition this specific tree with these specific defects would break. So this is only technology that is not ready for use today, or at least I didn't see it anywhere. But this is definitely something to look forward to within the industry that will be again enabled first based on the LiDAR scanning of the whole trees, but then also with 3D reconstruction of these elements. Yeah, and then again another study that same modeling would enable you to reconstruct trees under different wind conditions and how they grew, and better understand that relationship between wind and tree growth. So these are the topics I'm definitely interested about in the future. Okay, so this was, I have here, sorry, I have here a couple of more slides just describing how these trends are being programmed separately and how it can bring another limits, or not bring, but solve another limits of current tree biomechanics, which is, for example, multistems or codominant trunks, right, with the bark growing into it, or complex cavities, or even potentially tree dynamics, right? So this approach would really help us to push the industry forward in this regard. and model all sizes and shape of trees we simply cannot calculate today. Yeah, that was all from the presentation. I have here my LinkedIn QR code if you want to stay in touch, and I'm happy to help. If you are looking into LiDARs, happy to help you navigate which tool to buy, which not to buy, or just push you in a right direction if you are looking more into 3D scanning. But yeah, excited if there are any questions.
Thanks, Andre. That was super fascinating. We did have a couple of questions that came into the Q&A. The first one from Tim: when using the tree-mounted sensors, what are the limits of the scans above and below the mount points?
So this is, yeah, if I understand the question correctly, this is, yeah, if you are using LiDAR that is mounted on, for example, a vehicle, what are the limitations? And the answer is that it can model only what it can see. So it is reflecting the laser. So you can think of it as a laser pointer that's reflecting from objects. So for example, if you are driving car next to the tree, you not gonna get whole 360 of it, right? You are always missing that backside. But if you have handheld LiDAR, you can really walk around the tree. The same limitation with a drone. With a drone, it's great. You can have tops of the tree and most of the canopy, but you are usually missing the DBAs and the trunks altogether, right? So it really depends on the use case you want to use this technology for. And based on that, look into the sensor and the vehicle you can mount it on, or just using handheld.
Besides mapping things like cavities, are the dedicated, more expensive LiDAR devices capable of identifying other pertinent data, such as included bark and cracking, stub cuts, trunk damage, different colors to indicated chlorotic leaves and/or disease, etc.?
So there is interesting research in this area, but I would still take it with a grain of salt. So I would still be leaning on the side that they are not, even though there is a good research that can, for example, tell many tree species just based on the bark elements, and the structure of the branches and so on. But yeah, right now the data or our interpretation capabilities are still pretty low as an industry altogether. There is a potential, for example, to find deadwoods in the canopy, or I don't know, broken branches or big fruit bodies of fungi. But yeah, it's never gonna, in my opinion at least, it's not gonna be able to replace, like thorough consultant with boots on the grounds anytime soon. So yeah, if this is the question, I would be too afraid.
Have you assessed the live crown ratio and the and/or mass wind damping?
Yeah, so live crown ratio can be definitely calculated if you are from the handheld LiDAR standpoint. If you are collecting the data during the when the leaves are on. And sorry, what was the second question? Second part.
Sorry,
I can open it as well, I think.
Well, I just moved it to answer. So have you assessed live crown ratio, center of crown to overall height, and/or mass wind damping?
Yeah, so the damping is an interesting one because no one can actually right now, calculate it properly, or there are no studies that would go in such depth. But with the last approach I showed you, the spaghetti model, this is actually like quite promising that it could model tree damping as well. Because if I understand it correctly, there is variety of opinions on that. If you reduce the size of a crown, if it's helping the tree react to the wind load, or if it's hurting it. The typical approach of tree biomechanics is helping the tree because you are reducing the center of gravity, which, as I showed you, is the most important indicator of that weakest spot. And you are decreasing the size of the sail where the wind can, bend the tree and so on. But the damping meaning is that the you are reducing the tree's possibility to react dynamically on that wind. So yeah, there is like unclear relationship on how much actually dumping is helping the tree or not, in which cases. So there's definitely needs to be more research done on this, but I think this is the right way for the research to focus on.
So as a summary, which methods currently available do you recommend for assessing tree safety / stability? It seems like buying an iPhone.
Yeah, like buying the iPhone is the cheapest variant. So yeah, that's definitely a good starting point. So, you know, for $200, you can buy used iPhone 12 Pro and you are good to go for LiDAR scanning. And as your business grows in this regard, if it does, you know, looking into bigger LiDARs, and if you are doing more tree inventories, would be definitely an option. But I think for singular trees, the iPhone is way more than enough to start with.
Is the data analysis reliable, showing cavities do not present significant risks?
Sorry, I've got created in a chat, and yeah, could you repeat it, please?
Is the data analysis reliable? And then in parentheses, it says showing cavities do
Yeah.
not present significant risks.
Yeah, I would say so. Like there is more research on this than from ourselves. So I would definitely look into it more. And again, it's not black and white. I just wanted to show that, you know, for some trees, at least what biomechanics says, for some trees, it can be a problem. For some trees, it doesn't have to be. So it's not about being black and white, like cavities is bad thing. It's about analyzing more and figuring out, like, for this specific tree, is this specific cavity a problem, or can this tree continue for like several more decades where he is, right? So there is definitely some research other than ours that says like the cavities doesn't matter as much as we think they are. So yeah, definitely I'm leaning towards that opinion. But again, it's not black and white. Doesn't mean like every tree with cavity is safe.
This would have good applicability to model an estimate of tree failures during hurricane force winds, factoring in Cat 1 to Cat 5 into a tree and an inventory database. Is the programming and data analysis compatible with doing this type of calculation?
Definitely. So this is basically what we are doing in AdBN. It's like modeling specific wind load or highest wind load in the area to the model, and telling like what is that point where the tree would probably snap, and after which wind load. We are not modeling automatically like level 1 to 5 hurricane wind speeds, but for example, our approach is using building code, because building code basically tells you for which wind speeds you should build your houses for, right? So it's highest wind speeds in the area in the last 50 years. And we are using this value to calculate the wind loading. And yeah, in some areas such as Florida, this is like close to level 1 hurricane wind speeds. But yeah, I would say when tornado comes or these wind speeds, you know, every tree is gonna break. So we have to draw the line somewhere. And as my friend Simon Stratford says, like only safe tree is the one on the ground. So we always, you know, need to work with some level of potential risks, because the benefits of having healthy tree always like overweights it.
Just a couple more questions. Have you looked into maximal randomness, the model proposed by Emmanuel Villermo? My French is terrible. Sorry, Villermo, a French physicist at Marseille University. Do you think this model will apply to explain how breakage happens in trees?
I must say I'm familiar with the name, so I will definitely do some more digging. So yeah, I'm not familiar, so can't really respond to the rest of the question. But I definitely am. I'm definitely hopeful that this approach could show exactly like why, not why, but how and where the trees are breaking. But it's always important to, take it with grain of salt, because insides of the trees can be like very complex, and you can have like small cracks that we will probably never be able to model precisely. So I would look more on biomechanics as something that helps us safely push that boundary of what we are considering acceptable risks, or safe for trees, than something that's gonna one day tell us like this tree gonna break exactly here under exactly these conditions, because we are still assessing living organisms, and the complexity is just beyond any traditional like computational model.
We did have a request for you to go back to the slide right after tree biomechanics triangle of stability. And while he's doing that,
Okay.
we are just over time. So while he's doing that, I'm going to go ahead and put the link for the CUs in the chat. So give me just a second to grab that link, and I will put it in the chat. If you'll fill out this form, I will submit your ISA certification number to the ISA for 1 CEU credit. Again, we'll also have a recording of this available by the end of the week. Go ahead. Is that the they said right after the tree biomechanics triangle of stability.
Yeah, this is the next slide. So I have here triangle of stability, and this is the slide right after it.
Hopefully that will be the one that this person is looking for.
Awesome.
And that's it for the questions that we have this evening. Thank you, Andre. That was a super fascinating presentation. We really appreciate the time and effort that you put into educating our audience. Thank you all for joining us for this presentation this evening. We hope you'll join us for next month's webinar. And safe travels to you, Andre, as you go from Mexico to Australia.
Exactly. Yeah, thank you, Jesse. Thanks for having me. Thanks everyone who connected. And yeah, it was a pleasure connecting again, and hope to see this do this again sometimes in the future.
Awesome. We look forward to seeing you. Have a great evening, everyone.
Amazing. Great evening.
Thanks.
Bye-bye.
Bye.